Hey, it's Tony from Adafruit, and in this video we're going to look at MicroPython hardware and how to talk to SPI or SPI devices. That's Serial Peripheral Interface. And SPI is actually just a protocol for two devices to talk to each other, usually devices that are on the same circuit board because it's meant for like short distances. So like a microcontroller could talk to a sensor and read what the sensor sees, or maybe it could talk to an LCD display that's showing images and telling it all the pixel data. So the SPI protocol is a synchronous serial protocol. And we'll look a little bit more at that. And just to get started too, I've actually done a video on this before in the context of the Raspberry Pi and Python programming on the Pi. So I'll put a link in the description when this goes up on YouTube. You can go check that out and see a little bit more. I look at like a logic analyzer and look at, what does the signal look like at a low level. Really interesting. We're not going to get that deep into SPI, but I do want to look at how to use SPI with MicroPython. So you can write Python code that runs on a little microcontroller like the ESP8266 and starts talking to interesting devices like maybe an LCD display or a sensor. In this example, we'll look at the MAX31855 thermocouple amplifier. And a thermocouple is just a really nice temperature sensor. So it has a little probe and you can tell the temperature of it. And we'll look at that. It's a device that you have to communicate with using the SPI protocol. Real simple protocol though, so very easy to use. And we'll see if we can read some temperatures with it. So let's just kind of dive in and see what's going on. We'll do the main view here. So, okay, in the upper right-hand corner, so this is the device. It's the Feather Huzzah ESP8266 board, so real popular microcontroller. I've used this in all the MicroPython examples. And by the way, if you're totally new to MicroPython, look in the description. I'll have a link to the What is MicroPython guide. Check that out. There's a video that goes with it. It explains what it is, all different types of boards that use it, how to load it on a board, that type of stuff. So start there first. This is a little more advanced. But then connected to it is the MAX31855 thermocouple sensor. And then this little long kind of metal thing here, this is actually a thermocouple. It's just a K-type basic thermocouple. So on the tip right here, it's actually a couple pieces of metal. And the way it works is it can read, I believe it's the voltage will change slightly, and then it has to amplify it a lot so that you can tell that there's a difference. But based on the temperature change, it'll change kind of the values it reads out of the thermocouple. And they're very nice because they have a really wide range. You can get all different types of thermocouples. They're fast to react. Like there's not a lot of metal here to heat up. So if you put this into like boiling water, which I don't think this one's waterproof, but you can get waterproof versions. You can put it in the boiling water. It'll instantly tell you, 212 degrees. Just put it into ice cold water. It'll tell you, okay, this is like negative, 20 degrees or whatever. So really nice, fast reaction, super useful temperature sensor. Great if you're doing something like, I don't know, maybe like a barbecue or something and you're trying to measure the temperature inside of it, like a smoker. You could put one of these inside. Make sure to find like, food safe one or whatever. And then you can read the temperature, regulate it over time. And you could potentially start doing that with Python now, with MicroPython, which would be really cool. And then on the web page right here, so this is the Wikipedia page for SPI, for the Serial Peripheral Interface. So just skim this. This goes into a lot of detail. As a beginner, it's probably going to be a little bit overwhelming. But like I mentioned, I also did do a video a while back on this. So you can check this out and see. I went and do a deep dive here. Look at it at a low level, like with a logic analyzer, and see, okay, what do all the wires mean and how do they look like and things like that. So check that out. Man, I look a little bit different since back then. But then the focus of this video, this is actually to go with a guide that's going to be published really soon. It's not published just yet, but in the next day it should be published. And this is how to talk to SPI devices using MicroPython. So this is, boy, I don't know, 7th or 8th now in the series of MicroPython videos. So we've kind of covered the basics and are starting to dive in and talk to interesting hardware here. So we'll just kind of dive straight into it. This will actually probably be kind of a short one because there's really not too much to the SPI protocol. So I talk a little bit about it, and I make the distinction between a SPI master and a SPI slave device. And this is really just a concept of one device controls the entire SPI bus. So the SPI bus is made up of usually 4 pins. There might be less, there might be more, it really depends on the device. But at the very least, there has to be a clock line. And so this is a line that's driven up and down like it toggles. And that tells devices connected to the bus when they're ready to send and receive data. So they synchronize themselves to the clock line, and then the master device controls the clock line. So it will actually set it to a high level or a low level to tell everything else on the bus that, hey, get ready, start sending or receiving data. And then there's the MOSI line, the master output slave input. This is basically just the output from the master device. So any of the data that it's sending to a connected device, it will clock out on the MOSI line 1 bit at a time every clock cycle. And so you might think of this as like the data output from the master, and it usually connects to a data input on the slave device or any connected device for this. So again, the MOSI line is kind of the output from the master device. And the MISO line, the master input slave output, exact opposite. So this is basically for whatever connected device you have that's talking back to the master device, it will send the bits of data over the MISO line back to the master device. And so this is usually like the data output line from your connected device or the data input on your master device. So, these are the 2 kind of data lines for it. And you don't have to use both of these lines. Some devices like this MAX 31855, it only has an output. It doesn't have an input. So you can't even really tell it anything, which is fine. It just makes it a little bit easier. You don't have to use all of the pins for this. And then the last one most devices have is a chip select or a CS line. And this is just a line that you drive it to a certain value, usually a low value. Most of these are active low, but sometimes it's high. And the chip select basically tells the connected device that, start listening. The master is going to talk to you, or, it's going to expect to receive data. It tells that device that, okay, you are ready to talk to the SPI bus. And so like a SPI transaction might be setting the chip select to the appropriate level, clocking the clock line however many times you need, and then outputting and inputting data on the MOSI and the MISO lines, and then setting the chip select back to like an idle state for this. So those, and you don't have to have a chip select. I don't know of any devices that don't have one, but I'm sure there's some out there. But the nice thing with chip select is if every device has a unique chip select line, then they can all share the same clock, MOSI, and MISO lines. Each one needs a unique chip select line, which is usually just connected to a digital output on your board. But then that way you can at least share those other 3 lines, because only one device will be active at a time when its chip select is held to a high or low level. And so that way then, that only that device will use the rest of the wires on the bus, and everything else should be silent and just ignore whatever happens on the bus at that point. But you do have to be careful. Some devices are a little, like I remember the CC3000 had, it was like a open drain pin on the on one of the lines or something. I don't know. You have to like tri-state the chip select or something wacky with it. So every device is a little bit different. And with the SPI protocol in general, like, you really need to read the data sheet for your device and see how it works, because every device is different as far as how it sends and receives data. So I talk a little bit further down about a concept of polarity and phase. And if you go to the SPI Wikipedia page, it actually goes into a lot more detail here, where basically the clock line, a device might interpret a low signal as kind of active and a high signal as inactive or idle. And then another device might have the exact opposite polarity, where, a high signal is active and a low signal is inactive. So the polarity can change between devices. And then the phase is, when does the device send a bit out the MISO line, and when does it receive or read a bit on the MOSI line? And that could happen on like a rising clock edge or a falling clock edge. And so that's what the polarity controls. And so with those 2 different values, there are actually 4 combinations. And so there's this table of different SPI modes where it just changes the polarity and the phase depending on the different values for that. And again, every device can be different. A lot of devices use this SPI mode 0 with a polarity of 0, which just means that your base, your active state is a high level with the clock and it's idle at a low level. And then it looks like a phase of 0, it's going to read data on the rising edge and output data on the falling edge of the clock transitions. That's pretty standard, but again, you really have to look at the data sheet to see what's going on for your devices there. So that's what we're going to do. We're going to see how to talk to this SPI device. with MicroPython. And before I get started too, I should also mention, and I make a big point in the guide here too, the SPI interface, it's still, a little bit in development. It's complete, it works. It's just between each board, there are pretty big differences in how they implement the SPI protocol. I'm going to focus on the ESP8266 MicroPython, but for all of the other boards, definitely check out this bit of the guide right here where I try to just mention, you'll ultimately want to look at the documentation for your board, but there are some differences. The Pi board uses a different module right now, the PYB module. It also has a slightly older API where you have to explicitly tell it that you're creating a SPI master device. And then it also has slightly different named functions where it's called recv instead of read and send instead of write. So a little bit different, but the basic idea is the same. So, you'll still learn a lot of useful things here. You're just gonna have to slightly adjust the code right now. I think over time, hopefully, a year from now, we won't even worry about this and everything should hopefully be the same between all the boards. And again, the YPi, a little bit different. You have to tell it that you're creating a SPI master. And the microbit, it actually takes in a mode instead of a polarity and clock phase, but is otherwise pretty similar to the rest of what we'll see here. So, okay, so for this example, like I said, we're going to use the MAX 31855 thermocouple amplifier. So this little breakout board right here, real handy temperature sensor, very easy to use. And like I said, thermocouples are really nice. We actually have a guide on thermocouples. Yeah, this one right here. Oops, I didn't want to do that. Well, whatever. So if you've never used one, check this out. Lots of useful info in here. It talks about like the different types of thermocouples and how to use them, how to connect them, that type of stuff. So check that out. And then to connect to the board, it's really easy. Like I said, so we just use these basic 4 connections here for a SPI device. So you obviously need power and ground, so 3.3 volt power to the the voltage input on the breakout. Ground, you're going to need that for sure, so that's just the basics. And then the DO, the data output from the chip, that's basically that goes to the master input slave output, so the MISO line or the MI line on the Feather Huzzah ESP8266. If you're not using the Feather Huzzah, I mentioned on here, you'll need to connect to specific GPIO pins on the ESP8266. So the master input line is GPIO 12, and then the serial clock line is GPIO 14. And if it's not shown in here, but the data input line or the output from the ESP is GPIO 13. And this uses the hardware SPI interface, which we'll talk more about in a second. But anyway, so the data output, chip select, this just needs to be connected to any free digital output. So we'll just use pin 15 in this case, so, something you can set to a high or low level. And then the clock line, this gets connected to the clock line on the ESP board. So pretty straightforward and easy, just connect everything up to all the pins that we need. Obviously, you also need the thermocouple connected, this little wire thing here. And it does have there's a red and a yellow wire. Make sure to connect them to the right ports of the little terminal block right there. So, okay, so you do that. And like I mentioned, there is a concept of a hardware SPI interface, which is basically hardware built into the MAX 31855 that will do the SPI protocol for you. So it will actually, drive the clock line. It can drive it at really high speeds. I don't know what the limit is on the ESP, but I've driven it, I'm doing this at 5 megahertz, which is pretty fast. I'm sure it can go quite a bit higher than that. But that's kind of in comparison to a software SPI interface, which is a SPI protocol just bit banged or that you'd manually implement over any digital GPIO pins. And so the difference between those is really, with hardware SPI, you're usually limited to some fixed pins on the breakout board. So, there's certain pins that are connected to the SPI hardware, and you have to use those pins, like the clock line, the output, the input, those types of lines. Whereas with the software SPI, you can use any digital lines because you're just creating digital outputs on those lines and driving them high and low, or maybe making a digital input for the input line. And just there's software running on the CPU that's controlling those lines and implementing the SPI protocol. Now the issue is, it's not going to be as fast as hardware SPI. So, because their code on the CPU is running and it has to explicitly control those output lines, and it's only so fast that can run. So you're not going to get the highest speed, but you do get a little bit more flexibility. Now in this example, I'm going to use Hardware SPI just because in MicroPython in general, the software SPI support isn't really universal. The ESP8266 does have a software SPI interface, and I actually give a link to it, so you can use it, but the ESP8266 only has, a handful of GPIO pins, so you're probably not going to be able to find 4 free pins. You're just going to end up using the hardware SPI interface anyways, I would bet. So, in the future, maybe something worth looking at, but for now, we're just going to use hardware SPI, and it seems to work pretty well. So it's, you're not like giving up anything by using hardware SPI other than having to use these fixed pins here. So, okay, so everything's connected. So let's just open up a REPL and get to it then. I'm going to connect to my ESP8266 with the REPL here. And let's just start with importing the machine module. And, again, this is like pretty much all the hardware API is in the machine module, except if you're using the Pi board, it's under the PyB module right now. So just over time, I think that's going to change. And then after you do that, now we need to create a SPI interface. And so you'll actually see, so this top line here is what you should try first, but this might fail. And I'll actually try this, and I'll show you. It's going to fail right now for me. So we'll say SPI equals machine.SPI. And then you have to give this parameter as a 1 to start with, and I'll explain more in a second. The baud rate, so this is the clock rate that you want to use. And in my case, I'm going to set it to 5 megahertz, so 5 million, and this is just a value in hertz. It's kind of weird why they call it baud rate, but I guess that's true. I mean, it's the bit rate that the clock is operating at. Polarity, this is the polarity value of the SPI connection. So for this device, I need a polarity of 0. And phase, this is the phase for the SPI connection. And for this device, I also need a value of 0. And again, you need to look at your data sheet and kind of figure out, how does it expect the clock line to be idle? How does it expect to read and write data? And you can kind of see this. Or if it gives you like a SPI mode, then you might need to look at that table on the Wikipedia page to interpret, okay, SPI mode 1 equals polarity 0, phase 0. Actually SPI mode 1 is, I think, probably polarity 1, phase 0, but look at the table and see. Okay, so I'm going to try and create this, and oops, I just hit the mouse wheel here, so let me go back. Now I see an error here, value error, no such SPI peripheral. So what's happening here is I actually need to run this line, and the difference here is that parameter, that 1, instead of a 1, I'm going to set a 0. And so the issue here is that there's actually a very recent change, like literally 4 days ago or 5 days ago in the ESP8266 MicroPython code, where this first parameter is the SPI interface that you want to use on the board. And if you want to use a software SPI interface, you actually set this to -1. And that kind of tells the code that, hey, I'm going to create a software SPI device. And then in addition to this, you actually have to provide the pins for the clock line, the output, and the input. But I'm not going to use that here. Now, the value of 1 is what you want to use when you're using the hardware SPI interface on the ESP8266. But that's only using the very latest code in GitHub that doesn't even have an official release yet, I think. At least it's not in the 1.8.3 MicroPython release. But eventually, once there's a new release, like 1.8.4 or above, then you'll need to start using this value of 1 right here. But for now, because I'm using the current 1.8.3 release, you actually use a value of 0 to specify the hardware SPI interface. And the difference here, I think the reason they made this change is that there's actually 2 hardware SPI interfaces on the ESP8266, from what I understand. And interface 0, they've decided to make the interface to the flash memory that's connected to the chip. And they don't really make that accessible just yet. Maybe in the future they will. So I think they wanted to kind of reserve 0 for that. And then interface 1 is kind of the user-facing one, or the one that you can use yourself. So that's why it's going to change in the future. So for now, try with value of 1. If you get this error, then your firmware is a little bit older, and try a value of 0 for this. So, hit enter, and okay, good, that works. So I've got my SPI interface. Now, I'm not done yet because this will only set up the clock, the output, and the input lines. This doesn't set up the chip select line. And so for that, I just need a digital output pin. So I'm going to set up a CS pin, and this is just a standard digital output. So machine.pin, pin 15 in my case, and I need to make this an output. So machine.pin.out type. And then I'm going to set this to a high level because for this device, the chip select line is active when it's at a low level. So I'm just going to put it at a high level to tell the chip, hey, don't listen, you know, I'm not doing anything yet. You're just sitting there idle, basically. Okay, so that's all I need to do to really initialize everything. And again, I mentioned here there are differences in how this stuff is set up. If you're using the Pi board or the YPi, they take an extra parameter to this constructor or this initializer. It's a parameter that tells it if it should be in master or slave mode. And I'll talk a little more later about that. But for those cases, you need to actually tell it you're in SPI master mode. And I think that's going to change over time. They have a new hardware interface where they're actually making the SPI slave a whole separate class. So maybe you won't need that in the future, but just be aware, you know, again, check your board documentation. And then the microbit, like I said, it doesn't take in polarity and phase. It just takes in a single mode value, and the mode implies both the polarity and phase. They actually show in their documentation a table that tells you how to map between those two, so just look at that. But the important parameters here, the bond rate, the polarity, and the phase, these are all the same between the boards. And so, you know, again, that comes down to what device you have connected to the SPI interface, and you'll want to set it based on that device. So in this case, you know, this little thermocouple amplifier, I looked at the data sheet, and 5 megahertz it supports. Maybe it goes faster, but 5 is plenty fast for reading temperatures. And then polarity and phase are just the values that you can find in the data sheet for that. Okay, so at this point then, so I've got my chip select line. Let's read some data. This is actually pretty straightforward and simple. So first I need to assert that chip select line. So I'm going to say cs.low. So at this point, that chip select line is now at a low level, and the max amplifier is now waiting for the clock signal to start changing, because the way that this chip works, you assert the chip select low, and then you basically do 32 cycles of the clock. So you read 4 bytes of data, 32 bits total, and then it's going to output this 32-bit value that has a few things inside of it. It has the temperature that it's reading, and then certain bits that indicate if there's a fault or something like that. So to read data from the SPI interface, you can just call the read function, and you tell it how many bytes to read. So I want 4 bytes, or 32 bits total. And so when I call that, I get some weird value back like this. And we'll come back to this. So I read the data, and so now I'm going to set the CS line back to a high level, because I'm done kind of with this transaction. Which is the general practice for SPI things. You know, you assert the chip select, you read or write data, and then you put the chip select back to the idle level. So that's basically what I did here. So let's do it again. We'll save this reading this time. So we'll assert the chip select, and we'll say, how about value equals SPI.read4, and then cs.high. And so now I can look at the value. And this is just printing out a byte string. So this /x is kind of the hex. Basically, you should interpret the next 2 characters as a hex value. In this case, this is just L, so this is like the ASCII value. I'll show you something you can do, though. If you import the ubin ASCII library, so in standard Python, there's a bin ASCII module. In MicroPython, it's U for micro, the microbin ASCII module, just because it's similar but not exactly the same. But inside of here, there's a very handy function, ubinascii.hexlify. I always love that name, hexlify. If you pass value into that, this will just print out the raw hex value. So here's the first byte. It has a value of 0.1 in hex. The second byte has 6C in hex, 17 in hex for the next one. Oops, I almost got it there. And then 80 for the last byte in here. And if I look this up, if I look at the, let's see, Adafruit Max 31855 data sheet, I'll show you, it actually shows you how to interpret all of those bytes. So, oops, oh no, I want to do the data sheet. Let me go back here. There we go, I want this thing here. And if you never looked at the data sheet before, they're pretty fascinating. It's worth looking at. Don't be scared off. They're usually all in kind of a similar format, and there's a lot of stuff in here, but there's usually only 1 or 2 things that you care about. You can actually see, like, this is the SPI timing that it's using, so it's kind of showing how it expects the serial protocol to work. Usually it mentions somewhere like what SPI mode it uses, so you usually have to read the datasheet to figure that stuff out. This is what I care about though. So this table right here shows all of the 32 bits that the device sends back and how to interpret them. So like these low 3 bits are kind of fault bits that tell you if there's some problem, like if there's a short circuit with the thermocouple, you know, things like that. And then there's like 12 bits of signed internal temperature data because it's actually measuring the temperature of the chip. And then there's also a 14-bit temperature value from the thermocouple, and that's actually the value that we care about here. So I want to pull this thing out and start looking at the data inside of there. But this is pretty easy though. Like I just called that read function, I told it how many bytes to read, and it returns back a string of those bytes. Now there's one other way to use the read to read data. They have a read into function that I talk about. So I'll demonstrate that one. So read into needs to take in a buffer, and then it will fill that buffer with the data that it reads from the device. And so I'll show you how to do that. So to create a buffer, we'll just say value equals a byte array, and you tell it how many bytes you want. So I want 4 bytes. So think of this as just like malloc creating an array in C. You're just creating some dynamic memory. So I have a bit of memory that's 4 bytes long that can store bytes of data effectively. So that's how you create a buffer in Python. And if I look at it, it actually shows me like there's nothing in here. It's just initialized to 0 values, which is fine because they're all just going to be overwritten by whatever I read from here. And so now it's real similar. So we need to assert the chip select line. And now I'll call spy.readInto, and I just pass it this buffer. I don't need to tell it how big it is because in Python it's smart enough to know the byte array knows how large it is, so it's just going to look at the length of it. So it's going to fill that up, and then I'm going to deassert the chip select line. And so now if I look at value, I see there's stuff in here. So like 01, H, 1790, something in here. And I can already kind of tell. So like this last byte, the last 4 bits are 0, which is good because the last 4 bits here are the fault indicators. So, everything should be okay. I don't see any faults that are turned on right now. So you can even already start to see some stuff. But anyway, so you can see how it just filled this buffer, this value byte array with those 4 bytes that it read. And so this is kind of handy. You might wonder like, well, which one of these should I use? And so the problem is, it might not be really obvious, but when you're calling this spy.read, it actually has to go and create a buffer because it's going to return back some object that has those 4 bytes that it read. And so to do that, it's got to go pull some memory off the heap, fill it with that, with the data that it reads and return it back to you. And if you're doing that in a loop over and over and over again, MicroPython is going to be creating a bunch of these objects. And it's garbage collected, so if it runs out of memory, it's going to go and figure out, okay, which ones aren't being used, and it's going to reclaim them. But that takes a little bit of time. There's a little bit of overhead whenever it has to do that. Like anytime it allocates memory, it might spend some time doing this garbage collection phase. And if you're in a tight loop and like talking to a device and really timing critical, you don't want that to happen. So that's why in a lot of cases, you can pre-allocate things by creating a buffer ahead of time. So if you know you're in a tight loop and you're going to be reading a lot of data, create all your buffers ahead of time. Then inside of that loop, use these functions that take a buffer. And I haven't looked too deeply into it, but I would assume that a lot of other things that deal with large amounts of data usually take in a buffer like this. So, use this buffer interface, and then that way, this read into function doesn't need to allocate any memory because you're passing it the memory to save this data. You've already allocated this buffer ahead of time, and you're giving it to it, and then it's just going to fill it with the data that it reads. So you can do that in a loop and not really worry about the overhead of like garbage collection and things like that. So again, just something to think about. Don't worry too deeply about this, if you're new to this. But it's just something to realize that, even though this is Python running on a microcontroller, it's still a constrained low memory environment. So you still need to think about and worry about the heap and dynamic memory usage and what are the implications of trying to use that a lot in your programs. And luckily with MicroPython, it's super easy. You can just allocate memory like this with one line. It's not hard at all. You can pass these buffers around. They know how large they are. So usually you hopefully don't run into buffer overflow kind of errors and things. Try things out. If you're just playing around and experimenting though, you can even, just use these simple read functions and everything will be great. Okay, so we received some data from the chip. At this point, we're kind of done. Like that's all you need to do to read data with SPI is just use the read or the read into functions and you're good to go with that. So, and just a note too, the microbit for whatever reason doesn't have the read into function. So it only has read. So just be careful then with microbit if you're doing SPI stuff. Okay, so I showed how to use hexlify. The next thing is let's just make a quick little function here to convert this into the temperature that it read from the thermocouple. And actually, I took this directly from this. This is the Python library that I created for the MAX31855 temperature sensor. This is for the Raspberry Pi. It won't work directly on MicroPython yet, but in the future, I'm probably going to have to go through and like revisit our libraries and make them support MicroPython. So at some point, we'll have a MicroPython library for this. But for now, you can actually just read this code, and I have a function in here, this read temp C, that I can basically just implement directly in MicroPython. So the way this works is it reads 32 bits of data just like I did. It does it differently because on the Raspberry Pi it's using a whole different library for it. But once it has the data, it just checks to see, are any of these fault bits set? It's actually looking for this fault bit right here. If that's a 1, then one of these other values must be set. So it's just an easy, quick way to check if there was an error or not. But it looks to see, was the fault bit set? If it was, I just return not a number, like just some way to indicate that something's wrong. You're not getting a good temperature value back. And then I just look and see, is this sign bit set? So there's a bit right here that says if it's a positive or negative value. And then depending on that, I just do this 2's complement myself by just subtracting a value, just because it's a 14-bit value. And so it's a little weird. There's nothing, I think, as far as I know, natively built into Python that's like, interpret these bits as a 14-bit signed value. You can do it for a 16-bit signed value with the struct module, but the 14-bit, it's not going to work. So I just did it myself. But basically what I'm doing is I'm just shifting over 18 bits, which if you look at this, the first 18 bits are basically just going to cover everything up to here where the temperature data starts. So I just chop all these off, look at these upper 18 bits, I look at that sign bit, and if the sign bit is set, I just do a subtraction to make sure to put it into like a negative value. And if that sign bit's not set, then all you have to do is shift the 18 bits over. And then you multiply by 0.25, because the way this chip works, the value you get back is in like a 25th of a degree Celsius. So you just multiply by that and you get your temperature. So let's just implement this function here. So like I show basically exactly that function. It's just, it takes in that data byte array that I created here, or I guess I called it value in this case, in this example. But it takes that in, and then I'll explain as I implement it here, as I type it in. So we'll just go right here. Maybe I'll adjust this a little bit. So okay, so let's create this function, temp underscore C, and it's going to take in some parameter data. And then the first part here is I grab the first 2 bytes and I put them together to create a 16-bit value. So I'm just using bit manipulation here. So we just say I create this temp variable and I grab the first byte and then I shift it over to the left 8 bits. So I move it into the top 8 bits of a 16-bit value. And then I OR it with the next byte. And so basically this just means the first byte will be the upper 8 bits of the 16-bit value, and the second byte will be the lower 8 bits. And this pipe character is just like a Boolean OR, which is almost like an addition. So it just takes 2 values, and this value right here is going to be 16 bits, where the upper 8 bits are set to some value and the lower 8 bits are all 0. And then because I'm doing an OR with that, because all of those lower 8 bits are 0 on the left-hand side here, it will set any of those bits to 1 wherever they're set to a 1 in the lower 8 bits. So it's just kind of jamming these 2 values together. A very common thing you'll do a million times in embedded programming like this. Okay. And actually one interesting thing too that I saw in a presentation the MicroPython creator gave, where he's talking about different languages that run on microcontrollers, and the Lua language is a real popular one, like the Node MCU project. But apparently Lua didn't have any of these binary or like bitwise operators until like just a year or so ago apparently. So that's quite a challenging thing to do, like embedded stuff, if you don't have kind of these bitwise operations. But anyways, okay, so now let's just check if that fault bit was set. So if temp and OX0001, I actually could just check OX1. I just want to check if the very first bit is set in the 16-bit value. And oh, sorry, I guess the landscaping guys are around, so you might hear some leaf blowers and things going on. Maybe you won't, who knows? We'll see how good this shotgun microphone is, if it can hold the volume back. But anyways, I just figured I'd be explicit here to just really remember, this is a 16-bit value, and I really just want to look at the last bit, because if I go back to this data sheet, this last bit is the fault bit right here. So I'm looking to see if that's set. And so by ANDing it with my value, this will give me a positive value or a true value if that fault bit is set. And in this case, if it's set, I'm just going to return a not a number float value with Python. So, okay, so that's that part of it. And then the next part is kind of the real magic of it. So we're going to shift over all of the values, basically just 2 places right now. So, oops, I need to do double, there we go. So this just moves my 16-bit value to the right 2 bits. So it's going to chop off, you know, if you remember, like I had these, basically these 16 values, these 16 bits right here, I'm going to chop off these bottom 2, the reserved one and the fault bit. So now I'm left with just these 14 bits of temperature data and the sign bit basically up here. So that's what this line does. And then the next line, I look and see, is that sign bit set? So real similar little bit check that I'm doing here. But in this case, I need to check against the first of the, or like the 14th bit effectively. So OX2000 in this case. And if that's set, then I just need to subtract to do this kind of 2's complement. There might be nicer ways to do this, but this is the quick and dirty approach. And then at this point, I just need to return my value multiplied by 0.25. So this is just going to do the conversion into Celsius effectively. So, okay, so I've got this function. Let's run it on the value that we read earlier. And hey, 20.5. That seems like a normal value. You know, I'm American, so I'm used to Fahrenheit. But my basic knowledge of Celsius, I know if it's in the 20s, then that's usually a comfortable-ish Fahrenheit value. So let's see what happens. I'm going to hold the thermocouple tip with my finger here, and let's get a reading again. So we'll do cs.low, and this will be fun. I have one finger to type with. Okay, now I'm going to do cs, or no, sorry, I want to say value equals spy.read, and let's read 4 bytes from this. And then cs.high, so we deassert the chip select line. And at this point now, let's call temp C again on value. Well, first let's just look at the raw value. See, you know, we should see a byte string in here. Yep, you know, and it's a good little check. Like, doesn't look like any fault bits are set, so that seems good. And then let's call temp C on value, and I get 30.75. So cool, that gets a higher value. And I guess let's do the conversion. 30.75 C to F. And let's see, there we go. So 87 degrees, so that's pretty close, you know, like 88 degrees or so. That's probably around what your skin temperature should be. So cool, looks like this is working. That seems like a pretty logical value to get back from this. Okay, so that's cool. And you know, I love that this is just straightforward Python code, almost exactly the same as the code that I use on the Raspberry Pi right here. I mean, you know, this stuff is basically the same right here. It just differs in how I read the data. You know, I'm using a different library for that. So really cool, and really just highlights the power of MicroPython, that, you know, I can just create a little function, very simple code and easy to follow for this. Okay, so the last thing, I'm just going to mention it. You can also write data out the SPI bus. You know, I'm reading data from a device right now. Very simple. You literally just call spy.write and then pass it a byte string. So I can pass it, you know, like 1, 2, 3, 4. Now, there's not even a wire connected up from the output to an input on the Macs, so it's not really doing anything, but trust me, it's clocking out the data on there, and you know, you'd use this if you're talking to a device. And then there's one other thing. There's a write read into function, which basically this does both a write and a read at the same time. And this is sometimes called a transfer in the SPI protocol. And so this is basically, you're outputting data on the Mosey line, and at the exact same time as that clock is changing, you're reading data on the MISO line. And so it just depends on your device. Like, some devices might expect like a whole kind of transaction where you write out a little bit of data and then you keep clocking the clock and start reading in some data at the same time. So in a lot of those cases, you do a transfer that starts with a few bits of data and then has some like 0 or null data that you don't care about that you write out, but then during that time you're reading in data. So again, really easy to use it. You basically just call, like here, I can let's assert the chip select line, and then let's call spy.write. Well, actually here, I need to create a value, a byte array again. So we'll say byte array, like this takes in a buffer, so you have to create a buffer again. And now let's call spy.write read into, And I'm just going to write out junk data, 1, 2, 3, 4 again. And then let's call, or let's give it the byte array that I had, that value. And then let's deassert the chip select. And so now I should have a value again. And then if I look at the temperature of that, we do temp C on value 21.75. So that seems normal. So, you know, this is basically just like I read the data, but then I also wrote some data at the same time. So check that out. Very useful, handy functions to have here to use for this. So then the very last thing, SPI slave. So I kind of punted on this in the guide because the ESP8266 doesn't support slave mode right now, but the other ports do, as far as I know. Like the Pi board supports it, you know, probably the YPi, and maybe the microbit also. I'm not totally sure on that. But basically, slave mode is just your device can act like a SPI peripheral. So it won't control the clock line. It's actually going to read the clock line and expect some other device to be controlling that clock line. But you can read and receive and send data, you know, using that as a peripheral device. But, you know, again, it's still really early days, I think, in MicroPython for this. So check out your board's documentation. If it supports SPI slave mode, give it a shot. But, you know, again, it's a little bit early. Maybe it works, maybe it doesn't. Although it probably works. Like they're very good about, you know, not putting in like half-baked things. You know, if it's in there, it probably works. So give it a shot and try it out. But anyways, that's all I wanted to cover. So I just wanted to show the basics of talking to a SPI peripheral, like this little MAX31855 thermocouple sensor, and you know how to get data from it. So this is, you know, the basics of talking to other devices. So if folks have questions, maybe throw them into the chat. And let's see, I'll jump to the main view right here. There we go. For this. Okay, let's see. So let's see, someone was asking, have you benchmarked performance of MicroPython against the Raspberry Pi? Yeah, really good question. I have not, so, you know, that's a great question. So one interesting aspect of that is that MicroPython actually runs just fine on the Raspberry Pi. I haven't tried it, but there is a Unix port of it, or a POSIX system port, so it should run on the Raspberry Pi. You'll probably have to download the source code and compile it. That might be a fun thing to try later, because it does have an interesting implication where, you know, you could build something that maybe you run on a little microcontroller like, you know, the Feather Huzzah, write it in MicroPython, and then maybe you run into limitations, you run out of memory, or you want to do more advanced things, and you see, hey, a Raspberry Pi Zero is this $5, you know, gigahertz computer. Okay, let's try that. And if it can run MicroPython, in theory, your code would port over very easily to that. Now, you can also run the normal Python, but it is cool to be able to run the micro one, because the micro one might be a little bit faster. You know, it's just slightly more optimized, especially for low memory environments. So it's worth checking out. And I mean, from what I understand, a lot of the people that use MicroPython actually use the Unix port, or it is a popular thing for it. So that's kind of cool in the sense that, you know, if you want, you could use MicroPython on the Raspberry Pi, and then, you know, benchmark between the two. Yeah, great question. I mean, I can't really say for sure how things are going to work. I mean, it's kind of apples to oranges in some ways. You know, on these little chips like the ESP, it has a really lightweight operating system, a real-time operating system. So you don't have, like on the Raspberry Pi, you've got a Linux kernel that's doing all kinds of things in the background, and you know, it's doing all this advanced stuff. It's got a whole network stack and all this I/O and devices and stuff. But that might interrupt your programs. It's a little bit harder to do real-time kind of things with that. So I would say, yeah, I haven't tried it. You know, maybe give it a shot and see how things work. You know, I would say that they're probably at least similar in performance, you know, in the sense that, like, if you can talk to a SPI device with the ESP8266, you'll probably be able to talk to it with the Raspberry Pi the same way. You know, they might start differing in if you're trying to do like software SPI, like how fast they can bit bang the protocol and stuff like that. So, but anyways, yeah, I think that was the last question. So I'll wrap it up then. So this was Tony from Adafruit. This was looking at SPI devices with the MicroPython on the Feather Huzzah ESP8266. So check out links in the description. There'll be a link to this guide when it's published, when this goes up on YouTube, and you can see more details on this. So check out youtube.com/Adafruit. You'll see this video and all kinds of other fun project videos. Twitch.tv/Adafruit. That's where I stream this live. I like to do a couple live streams every week on Mondays and on Fridays. This week is a little weird. I did the stream on Tuesday because of the holidays, and I'm doing this stream on Thursday because I'll actually be down in Portland this weekend for all kinds of events. There's Mini Maker Fair, the Rose City Comic Con, and the XOXO Festival. So it's going to be a busy weekend in Portland, so I want to do this ahead of time. But then maybe next week, hopefully Monday, I'll be back and we'll look at I2C devices, which is another protocol you can use to talk to chips with MicroPython. So until then, this is Tony from Adafruit. Click the like, the comment, the subscribe button. Let us know that these are useful videos, and we'll keep doing them. So thanks a lot for watching. I'll see you guys later. Bye.